morning, M2. Welcome to our class. Today, for our computer science, we're going to review about computational thinking. Yes, review because we had this last year. I hope you still remember it. Let's go.
So, computational thinking. What is computational thinking? We use computer to solve problem, right? But before we can use computer to solve problems, we have to understand what the problem is, develop a possible solution, then present this solution that both human and computer can understand. So that is computational thinking. Understand what the problem is, develop a possible solutions, then present the solutions in a way that human and computer can understand. In other words, computational thinking is problem solving skills. Computational thinking has four techniques. These are decomposition, pattern recognition, abstraction, and algorithm. For us to understand better if what is computational thinking, let's watch the video.
Computational thinking. What is it, and why is it so important? Let's start by looking at the what. You may think that computational thinking is about thinking like a robot or programming like an expert. But it's not. Rather, it is a very versatile skill, a skill that focuses on critical and logical thinking. To put it simply, computational thinking is a problem-solving skill. Let's dive a little deeper. Computational thinking is about looking at a problem and solving it systematically, and therefore arriving at a solution that both humans and computers can understand. Essentially, it is considered the highest order of problem solving. Computational thinking is made up of four elements: decomposition, pattern recognition, abstraction, algorithmic thinking.
So this is the meaning of computational thinking, allows us to understand what the problem is and develop possible solutions. We can then present this solution in a way that a computer, human, or both can understand, just like what I explained. Let's go to the first technique of computational thinking, which is decomposition. What is decomposition? Let's watch the video about decomposition.
In computer science, decomposition is the process of breaking a big problem into smaller, manageable parts. Although decomposition is a proven technique for solving programming problems, this divide and conquer methodology can also be used to solve other everyday types of problems. For example, if you were baking a cake, you would need to answer the following questions. What type of cake will I make? Do I know the recipe? Do I have the ingredients? What will I cook it in? The answer to these questions will lead to additional questions and tasks. But eventually, if you persist, breaking the large problem into smaller problems will enable you to bake your cake. You've just reviewed an example of using the decomposition process to plan for making a cake.
So decomposition involves breaking down a complex problem to make it easier to understand. When I say complex problem, complex means big or complicated problem. So decomposition, breaking down a big or complicated problem to make it easier to understand or easier to manage. Let's have an example. Example, shopping. Example, your mom asks you to buy something. So, how do we break that down? How do we decompose that task? Number one, what we have to consider the budget. How much money do you have? Number two, what are the items that you should buy? Third, where are you going to buy? Are you going to Lotus? Are you going to Central? Are you going to the mall? And plus how to get there. How will you go there? Are you going to take a bus? Are you going to take a taxi? So this is the composition. You break down to make it easier to understand. Let's have another example. Solving a crime. How do we decompose this task? What are the things that we have to consider? How do we break this problem into small parts to make it easier to manage? We have to consider what. What was the crime? We should ask what was the crime. Another one, we have to consider when did the crime happen? What else? We also need to consider where did the crime happen. What else? We also need to consider who is the victim and who are the people involved in the crime. What else? We have to consider if there are any evidence in the crime. Have there been any similar crimes and who are the witnesses? So that's how to decompose a task. That is decomposition. Let's go to the number 2 technique of computational thinking, which is pattern recognition. What is pattern recognition? Pattern recognition involves finding the similarities or pattern among small decomposed problems that can help us solve more complex problems. Okay, look at these cats. I have 3 cats here. What are the cats' similar characteristics? What do they have in common? Try to think. What do they have in common? Here. General characteristic or what do they have in common? Okay, they all have eyes. Yes, they all have tail. They all have fur. They all like fish rather, and they all make meow sound. So these are general characteristic or the pattern that they have, that these cats have. If we have general, we also have a specific characteristic. What is the specific? Wherein they don't all have. Let's see. Eye color. This, the other one is a blue eyes. The other one is yellow. So the eye color, they all have eyes, yes, but they have different eye colors. I hope you understand. Next, um, tail length. The length is the other one is longer, the other one is shorter. So that's the specific characteristic that they have. Another one, the fur color. They have different fur color. And the other one, the sound. How loud? Yes, they all make a meow sound, but maybe the other one can make louder sound. That is pattern recognition, finding the similarities or general characteristics among small decomposed problems. Now let's go to the third one, which is abstraction. What is abstraction? Abstraction involves filtering out, essentially ignoring the characteristics that we don't need in order to concentrate on those that we do. So ignore what we don't need and focus or concentrate on the characteristics that we need. Example, our task is to draw cats. In order to draw cats, we have to consider the cat's characteristics, both the general and the specific. So these are the general characteristics that they have, and these are the specific characteristics that they have. So look at these characteristics, and then in order to use abstraction, consider what we need and we don't need in order to draw a cat. Relevant means the things or the characteristics that we need to draw a cat. Irrelevant, those are the characteristics that we don't need. So abstraction, focus on what you need, ignore what you don't need. So what are the irrelevant characteristics that we need in order to draw cats? First, eyes. We need to draw the eyes. We need to put the tail and fur. Those are just three examples. We need more. But the characteristics that we don't need or irrelevant, we don't need to know if they like fish, the cats like fish in order to draw cat. Yes? Another one, relevant one, the sound. In order to draw cat, we don't need to know the sound of cat. And how loud, same is the sound. So that is abstraction. Focus or concentrate on the things that you need and ignore what you don't need. Let's go to the fourth one, the last technique of computational thinking, which is algorithm. Let's watch the video to understand what is algorithm.
You may have heard the term algorithm recently, whether it was online or maybe in some conversation about technology. It's a word that gets thrown around a lot, but what exactly does it mean? Well, simply put, an algorithm is a set of steps used to complete a specific task. They're the building blocks for programming, and they allow things like computers, smartphones, and websites to function and make decisions. But in addition to being used by technology, a lot of things we do on a daily basis are also similar to algorithms. Let's say you want to make some spaghetti. In order to do this successfully, there's a certain set of steps you need to follow in a particular order. First, you need to boil a pot of water. Once it's boiling, you then add the spaghetti and cook it for a set amount of time, stirring occasionally. Once it's finished, you drain the water and then it's ready to be served with a sauce of your choice. That entire process is actually an algorithm. Because you followed those steps in that order, you reached your desired outcome, a delicious pasta dish. But if you were to make a mistake, say over or undercooking your noodles, it probably wouldn't be as good. Programs work in a similar way. Their code is made up of algorithms telling them what to do. Let's say that we want to use a navigation app to get directions. When we punch in a destination, the app uses an algorithm to look at the various available routes. Next, it uses a different algorithm to check the current traffic. And then a third one takes that information and calculates the best available route. All of these algorithms are built right into the app's code. If there were any kind of error in that code, the app wouldn't be able to follow these algorithms correctly, meaning you wouldn't receive your directions. Both of these examples show how both humans and computers can use algorithms to perform everyday tasks. The difference is that computers can use algorithms and calculate things better, faster, and more efficiently than we can.
So if you know how to prepare a meal, get dressed, then you already know how to follow algorithm. Because algorithm is a set of steps to complete a specific task or solve a problem. It is often used as a starting point for creating computer programs. To summarize the four techniques, which is decomposition, pattern recognition, abstraction, and algorithm, let's watch the video.
First of all, decomposition. Decomposition is about breaking a difficult problem down into simple and easy to manage parts. Second, pattern recognition. Problems come in all shapes and sizes. But amongst their many differences, there are bound to be similarities. Pattern recognition is about spotting what different problems have in common and using what's worked before to help you out again. Third, abstraction. Abstraction is all about focusing on the details that matter while ignoring the ones that don't. By applying abstraction, we can cut through fluff to get to the heart of the matter. Finally, algorithmic thinking. Algorithm is really just a big word for a set of rules. So algorithmic thinking is basically when you generate a series of simple steps that anyone can follow to solve a problem. Now, let's bring everyone together with a simple example. Meet Max. He's your average hardworking young man, trying his best to be a productive member of society. But today, Max's car has broken down. Luckily enough, he's computational thinking enabled. Let's see how he solves this problem. Max's car can't move too well. He realizes that there are two problems. He's running low on fuel, and he has a flat tire. That's the first pillar, decomposition. Now, Max has been in a similar situation before, and based on past experience, he knows that he should take care of the flat tire first. That's the second pillar, pattern recognition. He doesn't have much fuel left, but it's enough to get him to the next patrol station. So he decides to ignore that and focus on the tire. That's the third pillar, abstraction. Finally, to change a tire, Max has to use a jack to elevate his car, loosen the nuts on his tire, remove the tire, and replace it with a new one. Now that's algorithmic thinking. As you can see, computational thinking isn't just for computer scientists or programmers. In fact, many kinds of people, from mechanics, doctors, to presidents, are subconsciously applying computational thinking in their daily lives. Thanks, Max. Have a nice day at work. So why is computational thinking so important? It's not. That is, if you don't mind being left behind in the Stone Age. According to Moore's law, computing performance doubles every 18 months. That is to say, in 10 years, a $1,000 computer will be able to compute faster, more efficiently than the human brain. With technology growing at such an exponential rate, we are integrating computers more than ever before into our lives. To connect, to optimize solutions, and most importantly, to solve problems. The possibilities are limitless. The problem is, having a supercomputer carry out basic instructions and tasks is not at all economical. To make full use of a supercomputer, you'd need to know how to give super instructions. This is where computational thinking comes in, a powerful way to generate advanced solutions and manipulate computers to work for you. Now, imagine if mankind had such immense power at our fingertips. We would be solving problems faster than ever before, with laser accuracy and machine efficiency. With computational thinking and supercomputers, the dream to tackling titanic problems such as finding a cure for cancer can be a reality, pushing mankind beyond the final frontier and boldly go where no man has ever been before.
So that's all for now. If you have any question, please feel free to send me message. For now, you are going to have a quiz game. I prepared online quiz game about computational thinking and you're going to use Kahoot. If you don't know how to play it, you can watch the video on how to play Kahoot I posted in our Google Classroom.